Hello all, welcome to the channel. Today's topic is hyperconjugation. This is the fifth type in the electron displacements and also the most powerful among all the effects. Okay, so it is a phenomenon which is nothing but the delocalization of the sigma electrons of CH bond. Okay, delocalization of the sigma electrons of CH bond that are attached to a pi bond or a p orbital. The CH has to be attached to either a pi bond or a p orbital. Then we observe the sigma electrons shift or delocalization from the CH to the pi bond. Such effect is called hyperconjugation, or it is also called no bond resonance. I'll explain why it is called no bond resonance, and also it is considered to be Baker-Nathan effect. These are the different names given for hyperconjugation. Hyperconjugation or Baker-Nathan effect or no bond resonance. Now, what are the conditions that we have for hyperconjugation to occur? The main and foremost condition that we have is it should have alpha carbon and alpha CH bond adjacent to either an sp2 carbon or any other atoms like nitrogen or oxygen. Let us see clearly with an example. So consider the example propene, which is CH3 CH double bond CH2. Now the main criteria or the condition for hyperconjugation is the sp2 carbon or a p orbital of either nitrogen or oxygen, etc. So here we have sp2 carbon because this carbon is sp2 double bonded, this carbon is also sp2 double bonded. Now if we split this in the form of orbital diagram, then we can write this as CH single bond CH2. Then this pi bond, we know that it is formed by the sideways overlapping of p orbital. So this is the p orbital that is formed by the overlapping sideways. So this will have one single electron, this will also have one single electron. For the representation wise, I am writing both in the upward arrow. So this is the pi bond that we can see. Now what do we have? We have an adjacent carbon. Now what do you call this carbon? The carbon that is directly attached to any functional group or a double bond, you call it alpha carbon. Now that alpha carbon has 3 hydrogens, so they are all called alpha hydrogens. So this alpha hydrogen presence will cause the hyperconjugation effect. So let us see, this is an sp3 carbon, so one will be above the plane, one will be below the plane, and the other will be on the plane. So this is the hydrogen. Now this hydrogen carbon hydrogen bond is formed by sp3 carbon and s orbital. So it is a sp3 s orbital bond formation, that is obviously a sigma bond because hydrogen has only s orbital. So now what do we observe here is this sigma bonded electrons are going to be shifted towards this side. So sigma bonded electrons are shifted towards this side, and whatever pi bonded electrons are there, those will be shifted towards this carbon. So accordingly we can observe the formation of CHH. Now this hydrogen, since it has only 2 electrons but gave out those 2 electrons, it will be left with no electrons, so it is H plus. Now since this bond got shifted here, now this carbon will get a double bond, then again this bond is shifted towards this side, so it becomes carbon single bond with 2 hydrogens and a negative charge this way. So now again if you observe, this will repeat, this comes to this side and this will goes to this side. Again the process happens with the other 2 hydrogens also. Since hydrogen is losing its bond by giving out its 2 electrons, this is considered to be a no bond resonance. So this happens with how many ever alpha hydrogens are there beside the double bond, that many number of conjugated structures are formed. Since there are 3 alpha hydrogens here, we can expect this to be happening 3 times in propene. Similarly, if there are more alpha carbons and more alpha hydrogens, we can observe more hyperconjugation effect. Now, because of the alternate carbon-carbon single bond and double bond, the bond length will vary. Bond length in case of propene is observed to be 1.48 angstroms. It is less than single bond and greater than double bond. So it is in between the two, that is 1.48 angstroms. And the bond order also will vary because sometimes it is acquiring single bond, sometimes it is acquiring double bond. So hyperconjugation can cause many changes in the molecule. Let us see the applications of hyperconjugation. Now let us see the applications of hyperconjugation, which is the most important part of this concept. Now if you find this video helpful, please like, share and subscribe and share it with your friends. Thank you. So let us see the first application, that is the stability of alkenes. So stability of alkenes can be calculated or told based on the number of alpha hydrogens, because as the number of alpha hydrogens are increasing, this is directly proportional symbol, this is alpha. So as the number of alpha hydrogens increase, the number of hyperconjugation contributing structures are going to increase. So hyperconjugation will also increase. So we have butene, that is CH3, CH2, CH double bond CH2. This is one butene, and we have two butene, that is C double bond C, CH3, CH3, this is CH and H. We need to fill the valency. Okay, this is 2 butene and that is 1 butene. So first we need to look at the double bond. So here is our double bond, we have spotted it. Now we need to look at the alpha. So whatever carbon is directly attached to the double bond, that is your alpha carbon. So here we have one alpha carbon. I'll change the color. So this is your alpha carbon, and for this double bonded system we have 2 alpha carbons. So this alpha carbon has 2 alpha hydrogens, 2 alpha hydrogens. For this it is 3 plus 3, 6 alpha hydrogen. So 2 alpha hydrogens indicate less hyperconjugation, 6 alpha hydrogens indicate more hyperconjugation. So obviously 2 butene is more stable compared to that of 1 butene. So this way hyperconjugation can be explained based on the presence of number of alpha hydrogens, and accordingly the stability can vary. So if you can see the order of different alkenes stability, then the least one will be ethylene, because it's the basic one with no hyperconjugation or alpha carbon, compared to propene. So as the substitution increases, then comes the disubstituted, then comes the disubstituted on one side and monosubstituted on the other side. Similarly, we can replace this hydrogen also with one more methyl, and we get CH3 twice C double bond C CH3. This is the increasing order of stability of alkenes with the increase in the number of alpha carbons. So this is mainly supported by a factor or the property called, phenomenon called hydrogenation values or heat of hydrogenation. So it is mainly calculated according to the heat of hydrogenation. Now what is heat of hydrogenation? It is the energy that is released when we add hydrogen molecule to any unsaturated compound. So whenever you are adding hydrogen molecule to any double or triple bond, the energy that is going to be released, because it's an exothermic process, such energy is called heat of hydrogenation. And what is the relation between heat of hydrogenation and the stability of alkenes? It is inversely proportional. So whichever alkene is stable, that alkene will release less amount of energy when hydrogen is added to it. So hyperconjugation explains the stability of alkene, and also it is explained in terms of heat of hydrogenation. So we can calculate the stability as well as the heat of hydrogenation with the help of hyperconjugation. This is the first application. Now the second application is the stability of carbocation. So carbocation stability can be explained by hyperconjugation. So what is a carbocation? Let us look at the ethyl carbocation, that is CH3 CH2 plus. Okay, so here this has, methyl has 3 hydrogens, carbon with 3 hydrogens, and this carbon has 2 hydrogens. And here this positive charge indicates what? An empty p orbital. When we were talking about the condition for hyperconjugation, we said that either there has to be an sp2 carbon or an empty or p orbital in hydrogen or oxygen or any species. So here we are considering carbocation with p orbital, empty p orbital. Now what we observe here is this bonded, this is the alpha carbon with alpha hydrogens. Now this sigma bonded electrons are given onto the carbon with positive charge or empty orbital. Hence we can see the shifting of sigma bonded electrons from hydrogen onto the empty p orbital in among the 3 hydrogens. This way the positive charge in the carbocation is stabilized by 3 alpha hydrogens. So as the number of alpha hydrogens increase, the stability of carbocation also will be increased. Cation increases with the increase in the alpha hydrogens. This way, if we can see the order, methyl carbocation is less compared to primary carbocation, that is CH3 CH2 plus. Then comes the secondary, that is CH plus with 2 methyl groups, CH3 and CH3. Then comes the tertiary, that is carbocation with the 3 methyl groups. This is the increasing order of stability because of the increased hyperconjugation. This is the second application of hyperconjugation. Stability of free radicals can also be explained by hyperconjugation, as in the case of carbocations, because free radicals are also nothing but the carbon with p orbital containing single electron. So there can be again the shift of hydrogen bond from alpha carbon to the p orbital. Hence it follows the same order, like methyl carbocation is less stable compared to primary, less stable compared to tertiary and secondary and tertiary. So this is the order same as that of the carbocations. So the next application is about dipole moment and bond length. So whenever we see hyperconjugation, suppose in case of methyl nitrate, the present example, we can see the alpha hydrogen bond is shifted onto the carbon nitrogen bond, and this pi bond is shifted onto the oxygen. Accordingly we are getting CH2 H plus with no bond. Then here we are getting the double bond. Then comes single bond with O negative charge here, and the coordinate bond is remaining as it is. So here, while we are getting the second structure from the first structure, what are we observing? Single bond is turning into double bond. Here single bond is turning into double bond, then double bond is turning into single bond between nitrogen and oxygen, and the charges are developed. In the first structure there are no charges, but in the second structure there is positive and negative charge. Now because of the development of charges, dipole is created, or the polarity is created. Because of the charges, polarity is created, and the dipole moment also will vary. Because of hyperconjugation, dipole moment is varying, and also the bond length. In the first structure, different atoms were having single bond and double bond. Now different atoms are having single bond and double bond. Now because of the shift of bonds between single and double, bond lengths also vary effectively, and we can see it in the experimental values as well. So these are the 4 different applications of hyperconjugation that we have discussed in detail. Thank you.